So our next speaker is Alex Orr, who's a master engineer at Broadcom Limited. Alex gave a very popular talk on Formal before for us, and so he's been invited back by popular demand. Alex has over 20 years experience in semiconductor design and verification, having worked for Pikachip, Audium, Nodal, and now Broadcom. He's human, makes mistakes, and considers admitting this to be the first step in becoming a better verification engineer. And his talk is titled Better Living Through Formal. Thanks, Alex.
This is not going to be as technical as the rest of the stuff you've seen there. This is going to be a bit of lighter. I'm the light entertainment really here. So, but let me introduce myself anyway. I'm sure a lot of you have met me one time or another. I'm a Dave, a design and verification engineer in the parlance. So I've been doing it for 25 or so years in various different startups. Not all of them still around. Working on Broadcom at the moment. Not working on Broadcom. I'm working for Broadcom at the moment, and I've been purely verification 5 years, but it's been a speciality of mine for quite a long time. So it's just now I don't touch RTL other than complain about it to people. Before Broadcom, pretty much all my experience was dynamic simulation. So, you know, the regular stuff, test benches, primarily constrained random stuff since like 2000 or so onwards. And like everybody else in the industry, we're migrating to UVM, whether we want to or not. And so, but what I'm trying to get across here is I'm a just show me the waves guy. Or at least I was. And as I joked last time I did this presentation, if you cut me open, I bleed red X's. I'm that much of a verification guy. Primarily, though, I really want to point out I'm an EDA user. I'm not an expert. I'm not here to actually sell any tools, whatever. I'm a guy who has to do this for a living. I have to use all of these tools and and get stuff out there in silicon. And when I put this line in about my future employment depends on pragmatic and timely application of methodologies and tools, I was really rather helping when I put that in for review. They would say, no, that's too harsh. But no, apparently my future employment really does depend on actually applying this pragmatically. So I'll just recap the presentation that I did last year rather than make you all suffer through it again. It is on YouTube if you want to watch it. It's got lots of views, mainly myself. I'd say listening to my technique and listen to the pneumonia that I was suffering from at the time. But I first presented it last year at this very conference in 2015. And I'll run through the conclusions for you. So primarily it was that dynamic verification can really be seen as attempting to prove a negative. Effectively, all you can really say at the end of it, I've never seen this thing. And you've always got to kind of caveat it with yet. You've got coverage to give you some confidence in that. But, this is something which you're using your expertise. A lot of the art in what we do is that sign off and saying I'm finished. Formal verification, though, especially with the full proof type stuff, is you're getting a mathematically proven status. You're getting something that actually says, this is done. Yes, you have proven this. With a caveat, one of the things I've learned is that can still be wrong. Of course, garbage in, garbage out. If you write poor assertions and they prove, you can still be proving bad stuff. And that's one of the things to take into when you start touting about formal being this magical, mathematically rigorous proof. You can still badly form your assertions, and you can still, they can give you bad logic at the end of it. Formal verification has some real sweet spots. You've had lots of talks about arbiters. They seem to be the go-to thing for formal verification. And I think if you look at what Imagination have done in particular with like one assertion to rule them all, it really is a fantastic piece of IP. I was going to recommend everybody steal it, but he's patented it. So I'm guessing you might get into trouble for doing that nowadays. So, and arbiters, they can take billions and billions of cycles throwing at these things, trying to get them in all corners, where it really is, like just one or two assertions can prove all of these things. It really. So there's some sweet spots where you'd almost be foolish not to try and use a formal proof for. But dynamic verification also has its place in the world. We're not saying you should only ever use this approach. When you have proven that you've got a round-robin arbiter and like this, you still need to prove that that round-robinness is the right property for use at your top level. And dynamic verification really does suit a lot of this. We are throwing lots of packets around at the top level. You want to see actual application behavior. Have you solved the actual problem you're trying to solve, not just the mathematical, not just your mathematically correct implementation. So I would advise trying to have a mix and match approach to all of these different methodologies. One of the things I learned was I spent a lot of time trying to write the one true assertion that would capture them all. And I'm not an expert in SVA, so understandably I ran into some limitations. There were some bugs that got into the code because I am just not a great assertion writer. And there's no shame in writing some support code to do that. You should do that. You just do whatever you need to do to get the job done. And if a lot of that is just like behavioral code that sits around the outside, fine, don't worry about it. Just as long as it actually solves your problem, great. And of course, by doing that, you're lowering the bar of adoption as well. You don't need to be an assertion expert to actually get people in there. And as I talk more about where we might go with this formal, how to get it more widely adopted, I think lowering that bar will become important. Also, I think that formal verification has lots of applications beyond pure just proving your RTL. SDA constraints, the likes of that. I was talking to Synopsys before about some of the technology they have to actually to do some of this. But effectively, there are lots of parts in the flow beyond verification and the front end where actually, there are assumptions made about how this thing works, and they're not rigorously proven. And I think we could really push a lot of this stuff back and get other members of the larger Silicon community to adopt the formal approach. As I said, with the SDA constraints, often there's virtually no proof at all. It's literally the designer's word on the intent. And this is opposed to likes of UPF, where actually all of that stuff is understood now by the simulators. So you're taking your extra information, your meta information about exactly how your design intent, giving that to the simulator as well. That's not quite true of simulations and constraints. As we mentioned before, verification can, using formal for full proofs can be very, very fast. And it's really, really great for putting in the diag file where people are actually prodding around the design, they're exploring and stuff like this, because you get answers very, very quickly. The time to bug, which is a term which I learned at the Jug conference last year, is significantly shorter. And as mentioned also by Asa in his talk, that actually this is really, really great for continuous integration and sanity tests. That often the very first canary that tweets from your Jenkins run will be the formal proofs going wrong. Before you've even finished the actual elaboration stage of your design. So, these things are great because I used to joke that Jenkins will, kicks off a regression and it lets you know before you get to the car in your car park or whatever that you've actually, you've broken the build and you better get back in and fix it. Actually, you probably haven't got time to get your jacket on for some of this stuff. So, I highly recommend having in your sanity suites some form of formal, because it's usually the first thing to fire. Well, my ultimate conclusion was it's hard to imagine a modern flow, a flow describing itself as modern and robust, that actually doesn't have any formal verification element. And it surprised me when I was looking around and interviewed in various places, whatever, how few people actually, just a few years ago, had never used formal, or they had one weird guy in the department who did it and he left and nobody could understand his code, so we didn't really run it anymore. That was honestly the typical thing I got when I asked people about their use of formal. So, 1 year later, where am I? Well, I continue to use formal verification. I am an enthusiast rather than an expert, so hopefully that will protect me from the more dangerous questions I'm going to be asked. I love this stuff, but I'm certainly not an expert. I spent a lot of time running projects and telling other engineers what to do for the last year, so I haven't used it quite as much as I'd like to. But I'm finding, actually I'm using it more than I expected in lots of strange places that I didn't quite expect. As common to, I think one of the things we don't always do brand new designs. A lot of the designs we do are iterative or delta projects. Your B zeros and your C zeros and the like, as you're adding some features. And I'm finding actually formal's a great thing in there. We're finding that you've got lots of little things. You've got to add this to that, or prove this, or do that. And formal is a great way of actually getting in there and poking some of this stuff, and actually getting a very quick proof to stuff, enough to give you confidence to ship it further back down the chain. And it's making a lot of the more prosaic and more boring verification tasks, reverse connectivity, great, you get an existing netlist that's out there in Silicon, go and extract your connectivity again, and then use that to prove all your changes in there. Fantastic. And it's really becoming a kind of a standard weapon in the arsenal of the verification engineer, really. As I mentioned, I was a speaker at Jug. It's nice to get a bit of a jolly from work for all this. It was a great time out there. I saw Ashish spoke and Asta spoke as well. It was really enlightening for me, because I saw some really advanced applications of stuff. I realized my usage of stuff was very, very simple. I just do little proofs, whether they only take a couple of minutes to run. You know, we don't have any bounded proofs. You know, every now and again, some people just go on for ages. But hey, you know, we usually take the and out of the assertion and kick it in again, and it comes back. So, and some of this bug hunting stuff especially, I thought, it blew my mind. Seeing, you know, this, you're effectively taking the tool, and you're saying, go at it, go find me a bug. And you're using lots of cover statements in there, or I think typically 10x, what I was told, is what you use in these approaches, where you're telling the tools, this is what I'm interested in, and you just kind of let it go off. And I admit, I did say before, I don't care what engine, I don't want to care about engines at all. Now, obviously, if you're doing something specialist like this, you do need to know what engine you're using, and I can understand that now. Although I do still assert that if I'm just doing a simple proof, I really don't care. I just want to see passed after I've typed auto, or proven after I've typed auto proof. Well, this is amazing looking at this. In fact, this morning, actually, I was just sitting there thinking, actually, I've seen this before, and realized this bug hunting technique was what people had taught to me 10 years ago or so, when Formal was really very just starting. They showed me these tools. And I just couldn't get my head around it at all. It was too advanced, and I think that's perhaps the EDA guys. You might have to lower the bar for people like me when you're coming in. It reminds me of when constrained random techniques came out, and people were selling them as test bench automation. And people just couldn't get your head around what they were. And a lot of times people just went, oh, we'll just write more tests, or I don't understand this randomness. It takes time for people to get used to these techniques and to adopt them. Sometimes a lot of time. You know, now constrained random is what everybody uses, but it did take a lot longer than I think people in this room would like to admit for that to become a standard way of doing stuff. And I think similar with Formal. You know, especially these very, very advanced techniques. If you just put them into use and look what you can do, it just scares a lot of people. You just don't understand it. Certainly in my case, I just didn't get it. You know, I've known, for example, that the engine you need to use to do these things aren't looking for proofs, they're looking for failures. And that's an important thing if you just you just put assertions everywhere and it proves them, and then we can do this magic stuff, and it's like, oh, right. So, you know, the complexity of the tools is can be quite a little scary to some of us engineers, and it's easy to believe that you must be up and at that level, otherwise you're not a proper formal verification engineer. But I think, you know, and actually, in some places you do have dedicated formal engineers, but I think we can make a lot of gains by actually aiming it a little lower and actually just using it in its, spreading the use more and actually having, you know, being less complex. Now, I was looking for a way to kind of sum all of this stuff up, and I'd love to say there's a scholar of Chinese wisdom that I just came to mind immediately. Actually, I knew what I wanted to say, and I went and looked up something. But this really kind of pulls it together, I think. There's Sun Tzu, who's actually, I don't know whether he was some war philosopher or something like this, but he quoted by Gordon Gekko a lot in the 1990s. The expert in battle seeks his victory from strategic advantage and does not demand it from his men. Now, what does this mean? This means that if you're a real expert warmonger, you should be trying to win all your battles, not by having the best soldiers, not by having the best armies, but by actually making sure that the battles you have are really easy ones, or you get by surprise, so you don't have to fight at all. So the expert tries not to fight whatsoever. They don't go in there and say, well, actually, everybody has to be, you know, a fantastic warrior, and we win because of our ninja skills. Paraphrasing a little bit, perhaps. So let's turn this around a little bit and put it in our context. So the expert in verification seeks 0 bugs from best design practice and design for verification, and does not compel their team to verify harder. So that's what I'm trying to say here. We should really be trying to make sure that our job is easier, not that we are all super experts in the very latest stuff. Or to put it even easier and much more straightforwardly, put less bugs in the implementation in the first place for me to find. So let's empower our RTL engineers. You've seen this term before. Let's shift left. Let's start earlier. Let's share the love here, you know. What we want is we want to get RTL over that has, ideally, no implementation bugs at all, and we're only looking for divergences from the actual specification. So we want them to hand over better quality RTL and improve the state of it before it gets to us. And as I say, we only want to find spec divergences. We don't want to be finding, like, silly little implementation errors, because they take ages to debug. And if we get our RTL guys to use all of this, then often they'll find their own implementation bugs before 0 nanoseconds. So you don't even need a test bench from us. They can be out there proving everything that they see. And obviously, the way to do this is through liberous use of assertions and covers. And we should be compelling our RTL guys to say, well, if you can make a statement about something, these things are mutually exclusive. You should be putting an assertion in there, and you should be proving that. And we want to be putting all covers in our assertion, all of our decodes and transitions, and that, so they stand out from when we're getting our coverage and we're putting it together. And also, we want to find those holes before we, the verification engineer, fall into them and spend ages trying to prove them, or find out what the problem was. And let's use the mathematical rigor of these tools to our advantage. Let's let it do the De Morgans. You write it in your own natural language. Stuff which is easy for us both to understand, and let it tell you where things go wrong in strange and wonderful ways. Let's use this as a design partner. In some way, it's like having an omniscient minor deity sat there on your shoulder. It knows everything about your design. It knows that it can work all this stuff out. It's great. You don't need to do too much of the hard thinking here. Let the tool do that for you. It's got the better math. Oh. I pressed the wrong button. Sorry, I won't press that one again. Right, okay. And as mentioned before, we don't all get pure, 8.0 designs to work on. We all have to deal, if you're in any company with any, length of design, or any successful designs underneath their belt, you're going to have to deal with some legacy. And you're going to get this code that you're perhaps not familiar with. Perhaps the engineer has been run over by a bus or left the company, or whatever. But there's a good chance that you're going to get some code you're just not familiar with it at all. By using covers and assertions and loading it into a tool, you can go and prod and play with the what if and the analysis there, and actually go and figure out what the hell's going on underneath it. Find that parameter override hidden in a file somewhere. It really helps you understand what's going on with the design, and that shouldn't be overlooked. Just the pure joy of just loading this thing up, prodding around and figuring out what's going on without grepping the file all the time. And it's really easy to break a test bench by improving it. So you get given this stuff, you've got to add more to it. If you don't like that way that code's written, you try to rewrite it, you can end up with the right mess on your hands and everything apart. Now, obviously, you make sure that everything's all backed up and checked in, and you're in a state to be able to revert that. But you can get in a terrible mess with all this stuff. But you know what? You can add as many assertions as you like to all this stuff. You just bind them in, and you're not going to break anything other than perhaps the bugs that are lurking in there. Often we'll have a ticket for some missing coverage, whatever, that people have signed off on before, and they think it's important for us to capture it next. Well, we can use covers to actually see that we actually get that. We can actually reach that before we waste any time actually trying to get there. So this technology, and the reason I mention this is because, of course, this technology is legacy technology. It hasn't had the benefit of this approach before. So make sure we can actually get there. Great, you leave that in now. Now you've got something that's really easy to see when it's filled and easy to fill in your ticket. You can say, yes, seam coverage closed on this element, etc. Check in whatever onto version or Git or whatever. And one of the things you can also do, if you happen to have like some features, some bugs or whatever, like in Silicon, we can use the assertions to actually go and try and simulate them, because it can be very difficult to try and actually get to the scenario that you're actually seeing. But once you actually know what's going on in there, you can actually put an assertion, say, I want to see this design do that, and then let it do all the figuring out of how it gets there, rather than you trying to like sit there and first principle it all. And as I mentioned, I think there's lots of stuff in the back end where it's still a little Wild Westy. I think we should be proving all of our STA constraints, all our false and multi-cycle paths, often only reviewed by the designer. And they're an assertion about the design. I assert that this won't waggle when you're looking at it. And it's one of the reasons we're still running SDF simulations, this problem with constraint escape. And, like many isms, if you're not part of the solution, you're part of the problem here. Please, I've spent enough time sitting there last night at night watching the world's slowest test tick by with my boss saying, can we ship yet? Can we ship yet? SDF simulations I hate them. They're the bane of my life, And And of course, the great thing about spreading all of the assertions and all of this and putting them into the RTL as well, they'll fire if somebody improves the code somewhat. And so we get to see them early. So I highly recommend that you never put in a constraint into the back end that doesn't make it into the front end. One of the things that I've also found as well that often there's a lot of stuff that isn't in your RTL. It only gets in after, primarily DFT structures. And this is because the problem because some things are explicitly coded and you can go and verify them. But often you'll find that there's a well-meaning DFT engineer. He's got a lovely organized flow that involves a CSV file, because I love CSV files in Excel spreadsheets, DFT guys. And they will they don't have the skills to be able to run your test bench. They, especially if you're up in UVM land, they don't know how to extend your test bench and do that. How do you prove all of these things? Now, a lot of the automatically inserted structures will actually come with proper, the tools will test themselves, but there are some things which aren't. And we can teach them how to use assertions and teach them how to use the tools, so they actually put them in there and prove them for us. And that keeps them, it's much, much easier for them to get to know some rudimentary system Verilog assertions and to get them to know some rudimentary behavioral code than it will be to try and get them to, into UVM land. And we should also be trying to prove that test modes don't do anything evil to our code, so we can put lots of assertions in there. So when we get our netlist back, switch on a test mode, and all of a sudden, you're switching on 32 volts across all your sensitive transistors, we can detect that sort of thing. It's this sort of thing which falls through the flow as it crosses domains and boundaries between the different teams. And automation, it's really, really easy, because it's just tickle most of these tools on to actually spit out a JUnit file, which is just an XML. Put it in your Jenkins, and the speed of execution really, really helps your continuous integration method, because it fires really fast. So as I mentioned before, we should be adding a fall element to our sanity test, because it is fast and it is quick. And obviously, as been talked about many times before, stuff like UNR and unreachable stuff can massively help with your closure efforts, because it tells you where you need to refactor code, what's a real missing cover point and what isn't. So, bringing to my conclusions about this, I found myself using formal more and more, but not in the great big formal proofs or not in bug hunting, but actually just for day-to-day little verification tests. Because day-to-day verification tests often are, especially if you're the lead and you really can't commit yourself to the big glamorous part of the project, you get all the bitty stuff, and formal's great because we can just write these little things. We don't have to break any test benches, and I'm finding that it just makes my life easier. It's easier to do these Delta chips or whatever, which are actually the bread and butter of many, many companies. We're not always shipping brand new silicon all the time. And it's far less destructive than actually extending the test bench. We should be encouraging our RTL guys and people further in the chain to actually adopt formal and prove everything that they're sending to us. If we improve the quality, it makes our life easier. And we can concentrate on debugging divergences in the specification and not finding their silly little mistakes. And we all make them. And if we can get rid of SDF sims, I doubt we can get rid of them completely. Nobody's going to ship without at least doing a couple of them to make sure you're out of reset. But if you can reduce that test list to something much, much smaller, hey, I'll be up less late at night trying to sign off on these things. And there's plenty of scope for using this further down the chain. We shouldn't just think of this as just a design thing as well. We should be thinking about how we can test some of the FDA stuff and some of the test stuff and stuff like that. The stuff further down the back in the chain that doesn't really get that much attention from people skilled in coding and skilled in scripting. And ultimately, the best thing we can do to reduce bugs and make our lives easier is to help the RTL designers put less bugs in there in the first place. And that's the main takeaway. And that's the whole, I guess, shift left thing. And to that extent, Broadcom does, well, at least the part of Broadcom that I'm in, all of the RTL guys and all of the verification guys went on formal training this year. So we know that this is a great technology to help us as verification engineers by empowering our RTL guys. And that's all I really had to say. Thank you.
So we have time for questions. There's one online which I'll read out from Fabrice Beret. How many times did you find that the bug you found was because of a wrongly written property instead of a design bug?
Well, especially when I was learning, I found quite a lot of my properties with it. And of course, whenever you find a bug, there's always a negotiation that goes on between the design engineer and the verification engineer, unless you have a really great architecture department who can be an arbiter of them. And this is why I think that this idea about this methodology of having separate design and verification teams gives you a false sense of security. In reality, people have to get in the middle and argue over whose fault it is. So in the beginning, it was mainly mine, but we did find issues, didn't we, Tarek? Sorry.
Any questions? Yeah. Nothing too complicated.
Yeah.
Very easy.
Go easy.
When you're trying to do it in a day-to-day job on delta iterations of projects, especially legacy projects where you're making changes, how do you make sure the properties you're writing are for the correct requirements? Do you guys write a lot of specifications before you make the changes to the design?
It's interesting that because as somebody who comes to own a project that's a legacy one, I can either say to them, right, I'm going to assume that you found all the bugs, and then I'm only going to introduce new ones, and all your code is great, and I'll move on from there. Or I can spend the next year understanding exactly what you did, review everything, and then go through that with you. In reality, neither of those things are acceptable. You have to meet somewhere in the middle. So often things will be, especially stuff which has been seen in Silicon, will definitely be in a JIRA or whatever, and they're quite easy because it's a nice, easy thing to tie up. But yes, sometimes people do rewrite the specifications for whole new blocks, and that's, we do have to sit down there and review all that as if it is a new block, and review the verification of that as well. So, it's interesting. There's lots of design debt that you find in stuff like, for example, I'm working on a JTAG block, and it's obvious that this thing has been passed down Broadcom for the last 15 years or so, and all of the cost associated with that. And you need nice gaps in the project where you can stop and do extra things, especially for stuff like UVM. If you want to adopt that, that's really hard to say, right, stop, I'm going to take this down for 6 months, and I'm going to build a UVM thing and go from there. In reality, we're trying to add UVM to the flow and replace things as we want to, as we need. But Formal doesn't suffer from any of that because you don't need a test bench. You can just load it up and you can just add them in. You can just sprinkle around, and they're all sorted. That's one of the great things about Formal. It has that low overhead, and you can just add them in and dot them around. But yes, it is a review process. Yeah.
I've got a question as well, Alex. So it's amazing that your designer has also been trained in Formal. Have you done any metrics on how much use to make of it?
No, but it's interesting because when we added some things, or we ran ones which were only purely ran in the verification domain, and then I ran them, and then all of a sudden all these errors came out. They went away with a fun look on their face and sat down there and realized we discovered holes in there. And because effectively those assertions were never used by the designer, they were just put in there by the verification engineer for their own purposes. They start to say, oh, right, maybe I should just look at this. So we're finding it a slow thing. And Judd, one of the things that I found interesting was, whilst all the experts are all talking to each other, actually a lot of people are saying, how do we prove the value of this? How do we prove ROI? How do we say to people, you need to buy us more licenses for this? And I think I'm not sure we keep that accurate records of it, which will obviously help people buy in. And it's also very difficult because if you do encourage your RTL guys to do this, actually you're going to find you'll get less bugs because they're solving them up there, and you don't record oh, I typed this statement badly, whatever that line, before it gets checked in or before it gets in front of somebody else's eye, it doesn't get recorded. So I actually think, especially this kind of ad hoc usage, will be really difficult to prove that, other than the fact that actually us RTL verification guys will suddenly find less bugs and stuff. So.
Suggestion to you, Alex.
Hello.
You could possibly use the license checkouts from the design team.
That's a very good point. In fact, I just got my email today from the head IT over Fiora in Broadcom that gives me a Z-score that tells me exactly how many tools I've used. So actually, none of us know what it means and whether it's a good thing or a bad thing, or whether or not actually, if I use 100, 200% more than anybody else, does that make me a star performer, or should I? And actually, that's great because it clearly means we already capture all that sort of stuff. But I just get this bizarre email, and I realize now I can actually put that to use. I can actually see who's using it all the time. So.
Turn the data into some information. Okay, thank you very much, Alex. No more questions.